In today's lecture, we begin by describing the trapezoidal method for stiff differential equation. This has been used for both linear as well as nonlinear equation. While this is straightforward for linear equation, we will see that for nonlinear equation, we would require to have the solution strategy in an iterative fashion, and that makes it difficult, and we will also find out that sometimes it would even not work in that context. In contrast to trapezoidal method, we will basically talk about a new method which is not very old. It has come about over the last couple of decades. It is called the compound matrix method, and in this compound matrix method, we will see its versatility by talking about instability problems, and in the context of flow instability, we will be introducing what is known as the odd sum of field equation. This is basically a fourth order ordinary differential equation, which has been known for its stiffness, and this viscous instability problems would require a special handling, which was a very tough challenge and yielded solutions very efficiently by compound matrix method. We will talk about the eigenvalues and eigenfunction evaluation by compound matrix method. We were talking about a special class of ordinary differential equations, which are called stiff differential equations. Stiffness arises because of the feature of the differential equation, which admits of fundamental solutions which have disparate length or time scales associated with the variations. And for example, say if we are trying to solve this vector equation, the unknowns being from u1 to um, and you have prescribed, let us say, some kind of an initial condition u0, and what you look at in the analysis of the system, you work out this Jacobian matrix, that is the partial of f with respect to this elements of u. This being a mth order system, so you would get m eigenvalues, and if you stack them up in terms of the maximum and minimum of the real part. So, truly speaking, all these methods that we are talking about, you can use it equally well for real equations or complex equations. So, that is what you need to look at the real part of it. The real part will tell you how this particular component is growing or decaying with time, if say time is the independent variable, and you look at the maximum of such values and the minimum of it. The ratio is what we call as the stiffness ratio, and as an illustration we talked about Stewart-Landau-Eckhouse equation, where these A1s are basically complex quantities that you are looking at. So are these coefficients alphas and beta ij's, alpha I and beta ij's, they are all complex quantities. So, you can see that if we remove the coupling term, the last term here, or this middle term here, then you would note that the problem becomes somewhat easier. The stiffness does not come about, because stiffness is associated with coupled ODE. That is what we talk about here, that you have to have a multimodal system interacting with each other, or you can have higher order differential equations. You can write them down as a set of first order equations, and then you will perhaps get equations of this kind, and those ones would tell you whether you have a stiff system or not. So, if we remove this coupling terms, then it becomes somewhat simple and easy to solve. So, we talked about this example as a model, which shows that it has two fundamental modes. One decays rather rapidly as e to the power minus 2000 t, and the second one gently decays with an exponent of minus 2t. And if you try to solve this simple equation as it appears by the very best method that you can talk of, that admits a very small time step, because you have to resolve this variation. That restricts the time limit that you can advance your solutions. Okay. And this appears to be rather a small number, implying that you have to do a lot of work even to solve a simple equation like this, for which you have the exact solution. So, I may actually encourage you to get your hand dirty and try to really solve this equation yourself and find out what I am talking about, it makes sense or not. Now, of course, in this case the stiffness ratio is 1000, 2000 by 2. Okay. So, stiffness is rather high, and one of the method to circumvent the problems of stiffness was traditionally to adopt what is called as the trapezoidal method, and that is where we actually stopped. The trapezoidal method is fairly simple in concept, that if you have this, let us say 2 ODEs coupled here. Okay. So, the right hand side terms f1 and f2 continuously depends on time and this dependent variable y1 and y2, and we know those Jacobian matrix will give you a very disparate time scale. So, what you would do is basically try to take an average of this right hand side at nth time step with the current time step. What it essentially does, it actually smears those eigenvalues. Okay. The largest and the lowest averages out here, and that gives you a little freedom. Okay. So, this was traditionally done, and if you look at the model problem that we talked about in the previous slide, this is essentially a linear equation. So, adopting trapezoid method for this is straightforward. You just simply take the right hand side, average it out, and it is easy to implement if because explicitly then you can get what they are, because this will appear linearly here, and so this you can transpose on the left hand side and explicitly solve. And what happens by adopting this simple trick will allow you to increase your time step by a factor of 100. So, it is quite a big advantage that you can see. Now, what happens is when you have nonlinear equations, problem is not so straightforward, because then you end up with implicit equations, and that would imply that you have to adopt some kind of a iterative procedure. For example, if I have the nonlinear right hand side as symbolically written here, then what I would do is I will take the average of the previous time step where we have got the exact solution. So, I can explicitly evaluate this first term, whereas this term what I would do, I will be evaluating it in an iterative sequence. So, iteration counter is basically m. So, what I do is I take some initial guess, work out some next step value, then use that back here and then keep doing it, and convince ourselves that we have reached some kind of a convergence criteria. And once we have done that, so we are through for that time step, and this procedure has to be repetitively done for every time step, and you can understand that this will slow down the computation, and you also of course have to do a little bit of involved coding. That would be some additional chore for you to undertake. Now, while this was the situation for quite some time, a breath of fresh air actually came towards the late 70s. A new elegant method was evolved to tackle this stiff differential equation, and that is what I am going to talk to you about. This came out with this work of Ong and Reed, who were actually looking at solving problems of instability, solving eigenvalue problems. So, essentially you may have some kind of a linear equation, and fourth order equation happens to be a favorite for many physical systems. So, let us try to understand it with respect to this linear fourth order equation. you might think that linear equations are a piece of cake. It isn't. In fact, let me tell you, when it comes to fluid mechanics, where we spend quite a bit of our time, we notice that if we look at the generic nonlinear governing equation, that is your Navier-Stokes equation, that was solved even by desk calculator at the turn of last century. So, it was not that difficult, while the corresponding eigenvalue problem involves having to solve this linear equation. And tell you what, it was only in 1951 the first set of solutions were reported. So, you can understand that even though you may think that this would be easy to work on, it is not so. Consider the fact that these coefficients a1, a2, a3, a4, they are functions of y. So, these are variable coefficient ODEs, and they are quite difficult at times. And let us say your working domain ranges from y1 to y2. So, you would require auxiliary conditions. Fourth order equation would suggest we will require 4 of them. Suppose we have to solve an eigenvalue problem, then we would surely have homogeneous boundary condition, right, because this is a homogeneous differential equation, and eigenvalue relations require that you satisfy homogeneous boundary condition. Now, this is one of my favorite question I keep asking whenever I have the opportunity. Is there some kind of a black magic that you have a homogeneous differential equation and you have homogeneous boundary condition and you get a non-trivial solution? How does it happen? I mean, you have been taught this from your, if not in the high school, probably surely from first year, that you try to solve some kind of a eigenvalue problem. So, you have the differential equation, there is no forcing, it is homogeneous. The boundary condition is also benign, there is nothing forcing the system, still you get non-zero solution. How does it happen? I think somebody got really confused even comprehending the question, right? Shall I repeat? Okay. The question is simply is this: I have a homogeneous differential equation, homogeneous boundary condition, how do I get inhomogeneous solution? That is the basis for all your eigenvalue problem, right? What is repeated?
If you expand the basis vectors in function space, it's something like it's a Fourier series. We can express it as a linear combination of infinite.
So what happens? Still, I am asking even a more fundamental question. It comes from your physics. Talk about conservation principles. I have not done anything and still I am getting non-zero dividend. How does it happen? So, how does periodicity help there? And it is not necessary to always use Fourier basis. I could use any other functions, any other orthogonal polynomial would do, right? Well, think about it. It is not very trivial. This is something that mathematicians and physicists teach wrongly in schools. You give it to engineers, they will do better job. They will explain to you how this is done. If you look at it this way, suppose let us say we are looking at some kind of a differential equation like what we have written there, say phi n is a function of all kinds of derivatives all the way up to like this, and you are probably prescribing a set of conditions, say phi prime, phi double prime, etc., etc. You would have n such conditions, right? That is what you do is define as 0 for your eigenvalue problem. Now, if I trick this problem and instead make this some kind of non-trivial boundary condition. That is what actually happens in a real life. Although you talk about homogeneous boundary condition, you would not find any system that works in vacuum, right. You would have all kinds of environmental input. It is only that we cannot measure them. If you think back, even tossing a coin, ideally speaking, if you know all the inputs and if you know the actual governing equation, you should be able to solve it as a deterministic system. You do not have to toss the coin and hope for heads or tails. It is only that lack of our knowledge of the system, dynamical system, plus the lack of knowledge of the boundary conditions forces us, auxiliary condition forces us to take a statistical route. So, what we are saying that just because we cannot quantify the background disturbances does not mean that we have this always equal to 0. So, in most of the cases in real life system you will always have something forcing there. Even your differential equation, not all the processes have been modeled, and you know, in a dynamical system language this is what is called as the process noise, that our knowledge of the system itself is imprecise. Suppose I am tossing a coin, I do not know what happens if there is a temperature gradient in the air, or maybe some kind of a gentle wind blowing or some kind of a puff of gust is going on, they can affect the outcome, right. So, it is just that what we say, borrowing some central limit theorem, which we say that if there are infinite such inputs to the system which are independent of each other, the outcome is what you get as a normal distribution, and then you apply your statistics and thereby hangs the tail. So, now if I look at it this way, what I can do here, as we will shortly do, we will find that the solution that we are going to get, that would be something like the input times what we call as the transfer function times the input. So, if I call this as the input, so this is what we are going to get. So, phi will be some form of this kind, and now what happens here, this is what we are writing, this happens to be your characteristic equation or eigenvalue factor. This is what we will also call as the dispersion relation shortly. So, what you find that you try to find out those eigenvalues which corresponds to the 0 of this denominator, right. That is how you define your eigenvalue problem, that is how you do it. Now, what you can see is what it says, that such a system is a kind of an amplifier, because even if you give b to 0, then you still have a 0 by 0 form and you can get a finite outcome, right, finite solution. It is a 0 by 0 form, indeterminate form, but will give you some kind of a finite value. So, what it actually tells you that even if b goes to 0, this ratio gives you a finite quantity. That is your mathematical answer, that is how you define your eigenvalue problem. Physically, actually it means that you are not talking about the system in isolation. It would be the disturbance is drawing its energy from the lower order system. So, for example, if I am talking about flow instability, then I have a mean flow that is blowing, and then in that mean flow I am trying to see how the disturbances are picking up. So, when I am talking about this growth of the disturbances, they have actually virtually access to a pool of energy coming from the mean flow. So, it is not violating any of your conservation principle, because the disturbance energy taps its energy from the mean flow, and mathematically this is what you see, that is what is the reason that you get what we were talking about, that homogeneous differential equation, homogeneous boundary condition give you inhomogeneous solution, and that happens only for certain combinations of the parameters. That is what you call is your eigenvalues, right. So, Ong and Reed were really guided in their approach in trying to solve such problems. So, two of the conditions, let us say, are given here at the left extreme, which are homogeneous. The other two conditions could be homogeneous or could be something like the variable decaying to 0. So, phi and phi prime not exactly equal to 0, but going to 0. So, that kind of a condition would be given, and what we would do is what we have been telling all along, that even though it is a higher order system, we would write it as a set of first order equations. So, it is a fourth order equation. So, we can define auxiliary variables like phi prime, phi double prime and phi triple prime. So, this makes you a gives you a fourth order system, and what you can do is you can convert the 73 into a linear algebraic equation. Phi prime is some A matrix times phi, and this is what you would get. So, of course, phi prime, that is the first component. If you differentiate it, you get the second component, and second component you differentiate, you get the third component. The first three equations are straightforward from the definition itself. The fourth equation comes from the governing equation that we have written down. So, that is what you get. Now, as I said that it is a fourth order system. So, we will have 4 fundamental solutions, and let us say that 2 of them are physically admissible. That is what we say. Like we could let us say create, we have a domain here, and I am creating some kind of a disturbance here, and if we are talking about this as y, what I am saying that as I go away, far away from this, the disturbances would decay. So, if I am following a constant let us say x line, and I have got that differential equation like this, So, this is variation with respect to y for a fixed x. Then as I go away from the source, of course, those two disturbances would decay, and that is what we are saying. The other two conditions would be prescribed as a limiting condition, and once we convert this differential equation in this form, then we will have 2 of the solutions which will be let us say decaying with y, that we will take it as admissible solution. That is what we are saying. Let them be phi 1 and phi 2. So, they actually satisfy the boundary condition. You may find that the other 2 would not satisfy your physical conditions, that what we said, that it should decay with y. So, those 2 are of no concern to us. So, although this is the problem of parasitic error growth we talked about in the last class, that 2 of them are admissible and 2 of them are non-admissible, and if you do not pay attention and care, the numerical error, they could ride on those non-physical solutions, and that could explode and give you a totally meaningless result. So, what we are trying to do is, out of the 4 fundamental solutions, the ones which are admissible, we try to construct a solution matrix, which again we call, let us call them call it as phi, consist of those 2 solutions, phi 1, its other 3 derivatives. Okay. So, basically we have this 4 by 2 matrix. From there, what we could do is we could construct various combinations, 2 by 2 combinations. So, basically what we are talking about, I did talk about 2. Okay. So, this method that we are talking about is called compound matrix method, and in the compound matrix method we form the compound. Let us say, for example, we take care of these 2 rows, that will give you this variable z1, okay, phi 1 phi 2 prime minus phi 1 prime phi 2. Then if I do, so this is your z1, and now if I couple the first and the third row, I will get z2, and the first and the fourth row will give me say z3. Okay. Then of course, there are other possibilities, will be this 2 and this 2 and finally this one. Well, you can very clearly see that it is going to be 4C2, right, because you have 4 by 2 matrix. So, you will get 6 such combinations, that is what you get. And once you have obtained let us say Z1 as phi 1 phi 2 prime minus phi 2 phi 1 prime, I could differentiate it. I will get Z1 prime as phi 1 prime phi 2 prime plus phi 1 phi 2 double prime minus phi 2 phi 1 both of them like this, and phi 2 phi 1 double prime. Of course, this 2 will cancel, and this one is of course nothing but your Z2 itself. So, you get an equation from the definition itself that Z1 equal to prime equal to Z2. You could keep doing that, keeping in mind that that your governing equation is the fourth order equation. So, if I take Z3 prime, of course, you can see that there would be phi 2 4, and here we will get phi 1 4, and since they satisfy your governing equation, you can plug them in and work it out. You would see that you will get that as Z3 prime equal to A3 Z1 plus A2 Z2 plus A1 Z3. So, the same way we can work out on Z4 prime. Z4 prime will be again will not involve the differential equation. It will just have phi 1 prime and phi 2 triple prime and phi 1 triple prime and phi 2 prime. That would give you nothing but equal to Z5, and if you look at Z5 prime, that will involve the differential equation, and same way Z6 prime also will have this. So, you can see what we have done here. We have converted a fourth order system into a sixth order system. So, we have already decided to do little extra work. We have increased the order of the system, and what do we get? We will tell you shortly through an example. That is the way I like to communicate that this compound matrix method is generally developed to study problems of instabilities with basically the modes that actually grow in space and time. So, what happens is for such a system, instead of working on the original problem here phi prime equal to a phi, if we solve instead this altered system, compound matrix variable system, that is much more easier. So, let me just demonstrate this by an example from fluid mechanics flow instability problem. This equation was derived by Orr and Sommerfeld, and this is as you can see a fourth order, well, d is the operator d dy. So, you get fourth derivative here on the right hand side, and those of you who are familiar with little bit of fluid mechanics would recognize this coming from the viscous dissipation, whereas these are the terms which comes from convection. But let us not worry about fluid mechanics. Let me state it as simply a problem of stiff differential equation, and then let us see what we can do. So, basic problem is of this kind. Let us say we are talking about flow over a simple geometry like even a flat plate, and the flow is coming like this, and we have already done a few lectures ago that it creates a kind of a boundary layer, and we have talked about that solution as u of y. And now what we are seeing, that given that mean flow, we are trying to figure out what the disturbance is going to do, and this disturbance quantity defined by, let us say, the stream function. And for this problem, if I am talking about a simple 2D problem, then this is written down in terms of Fourier Laplace transform with the basis given like this. See, that is what I just now told a few minutes ago. In actual problem, if you really want to excite some kind of an instability, you would have to sort of give some kind of an excitation, okay? And we will talk about it. Let us say I put in a kind of a vibrator there to create disturbance, and this vibrator that we have, that is oscillating, let us say, at a frequency of omega naught. Okay? That is what this omega naught comes in here, and we are just trying to find out if that time dependent excitation creates some disturbance which grows in space. So, that is what we are looking for, alpha. So, we are trying to look for complex alpha which will be governed by this equation, the Orr-Sommerfeld equation. That is what you can now see, that phi is that. Well, I think I have used a lowercase phi. So, let us keep it lowercase phi, and then what we are going to do is obtain the solution given by that Orr-Sommerfeld equation for all possible values of alpha, and then integrate this. Well, those of you who are from mathematics department, you would recognize, or if you do not, this has to be evaluated along what is called as the Bromwich contour. So, not all contours in the alpha plane are admissible. You will have to find out which way the wave is going, and you have to construct a contour that does not violate physical principles. So, that is what we call as the Bromwich contour. But for rest of you, do not bother. I am just stating the problem. Physically, this is the issue, that there is a mean flow coming, and that sets up this boundary layer. That is your mean flow, and then we are creating a small disturbance at the wall, and we want to study how this disturbance is going to manifest itself in the flow field. And that is what this equation tells us, that the mean flow here, u and its second derivative are involved. So, you can see, that is what I was telling you, that in all disturbance evolution equation you would have input coming from the mean flow. It does not just evolve by itself. There has to be a source of energy from where it will tap its energy. So, that is how this mean flow terms come into this equation, and these are various mechanisms, that is what it does. And okay, so this is the statement of the problem, and as you can see, we have just shown how this has to be converted into a sixth order system. And the boundary conditions, well, I have written it down, phi and phi prime equal to 0, but if you give an excitation here, you do not need to do that. You have a specific finite disturbance being given there. So, that will change to inhomogeneous part, whereas if you go far away, from the source, you would require those disturbance quantities to decay, and that would imply the phi and its derivative to approach 0. It is not equal to 0, it is a different type of boundary condition, asymptotic condition. Now, to get a glimpse of what happens in a problem like this, we have seen that this creates a kind of a boundary layer. So, outside the boundary layer what happens? The flow would have reached its constant value, right. It would reach its constant value. That is what we are saying, that if non-dimensional value would be equal to 1 and the derivatives are all 0, right. If the derivatives are 0 and the value is, then although your governing equation is a variable coefficient ODE, in the free stream you will get this as a constant coefficient ODE. And once you get that, it is easy for you to start off with a given mode like this, e to the power lambda I y, plug it in this equation, and then you would get a polynomial for lambda, and 2 of it you will see they are given by minus and plus alpha, and 2 of it is given by minus and plus of q, where q is this. So, everything is obtained from this equation 77, and what you notice that what I told you, that couple of the solutions are admissible, couple of them are not. That is why I particularly demonstrated this example to you. Now, what happens is, suppose alpha is a complex quantity, and if its real part is positive, then what happens? One of the mode is growing with y, and that violates the principle. We said that if we go far away, it should not decay to 0. So, what you immediately notice that if I take the modulus of alpha, and if that happens to be if the real part of alpha is positive, then of course, lambda 2 is not admissible. Lambda 1 is admissible, because that is the solution which will decay as e to the power minus alpha y. Same way, you can see I am extracting a square root from this quantity. So, one of it will be positive, one of it will be negative, and the one with a positive real part would again grow with y, and that will be inadmissible. So, what you are seeing, that although it is a fourth order system, only 2 modes are admissible. That is one thing. The other thing is, most of these problems of instability arises when your this parameter here, the Reynolds number, happens to take large values. You know, for flows at low Reynolds number, you do not see instability. Instability is a characterized by certain range of parameters, and in this case it so happens this R e has to be large. Well, I have just shown you sort of estimate. It need not necessarily have to be infinity, but it should be fairly large, and if it is fairly large, you can see modulus of q is much larger compared to modulus of alpha, and this is the stiffness problem, because you have one solution going as e to the power minus alpha y, another part is going as e to the power minus q y, and now you can see the stiffness ratio would be modulus of q by modulus of alpha. So, that is why I chose this particular example to show you all the subtle issues involved in solving stiff equations. So, what you do is, of course, you write down the fundamental solutions in terms of all those 4 quantities. Those are possible from mathematically, but out of those 4 we have seen in the free stream this phi 2 and phi 4 grows with y, and they have to be removed. So, they are not physically admissible. Then what we are talking about, we should have the composite solution in terms of phi 1 and phi 3, which are admissible. Now, what we said that at the wall this phi and phi prime are 0. So, that gives us this condition, right. So, these are 2 equations for these 2 coefficients C 1 and C 3, and as I told you that if it was not a homogeneous boundary condition problem, then this right hand side would be non-zero. Okay. See, this will be non-zero, and then you can straight ahead solve for C 1 and C 3. Okay. So, that is one thing, but how do we get the characteristic equation? We say, look, I mean we are looking for those combinations of complex alpha for which the determinant of the matrix formed by phi 1, phi 3, phi 1 prime and phi 3 prime gives you a 0. So, that C1 and C3 would be right hand side vector will be 0, and if I take inverse of that matrix, that will give you a determinant in the denominator. So, that determinant in the denominator is this, right. If I switch back, you can see that is nothing but this phi 1, phi 3 and phi 1 prime, phi 3 prime. If I take that, that is what we are going to get, and that is your characteristic relation. We will also call that as a dispersion relation, and I will define what dispersion relation is. But looking at this expression, you can say what we are implying by dispersion relation. We are fixing omega naught, and we are trying to find out that complex alpha which will satisfy 79. So, it is not all alphas are admissible. You will pick and choose a particular set of values of alphas which we will call as the eigenvalues, and those complex alphas are the eigenvalues for this fixed omega naught and Re, right. So, this is something that we have to take home from here, that what is this quantity. Now, if I look at the definition of Z1, that is that quantity, right. So, the dispersion relation that we wrote down there comes about the first compound Z1 evaluated at the wall, that has to be set equal to 0. Okay. So, that is your dispersion relation. Okay. So, this basically is a statement of eigenvalue problem, and we can study it. So, if we now look at what we have here, we can plug this particular values, a 1 equal to 0, a 2 will be this, a 3 is 0 and a 4 is this, and what we need to do is develop a methodology of solving this problem. The methodology for solving this problem is the following, that your dispersion relation is that Z1 equal to 0 here at y equal to 0. So, what we try to do is then we try to start the solution from far away in the free stream, and then we march downwards. Okay. So, what you do is you assume some value of alpha, because you have already fixed omega naught and Re. You start from there, and your governing equation is this Z dot or Z prime, whatever we have written, times this B matrix times Z. So, that is the equation that we are solving. So, this Z prime will have those Z1 prime, Z2 prime that we have already evaluated. Now, what you have noticed, this is I am taking a little time to explain to you, was Z1 is this, right, and what we found that phi 1 in this case goes as e to the power minus alpha y, and phi 2 in this case goes as e to the power minus q y. We have worked it out, right. Now, if I look at this definition of Z1, so we are looking at Z1 for y going to infinity, there we have the fundamental solutions. You see, this phi 1 and phi 3, phi 2 is not the same thing everywhere. It is at that part of the flow where you have a constant coefficient ODE. That is why we could get that exponent. Inside, where u is not equal to 1 and u double prime is not equal to 0, we do not know what these exponents are, right. So, this is the issue that you have to understand. So, in the free stream, we know the variations like this, and we can plug it in there. What we are going to get? We are going to get phi 1 would be something like this, e to the power minus alpha y, and phi 2 prime will give us minus q or e to the power minus q y and minus e to the power minus q y, and if I differentiate it I will get a plus, and I will also get a alpha e to the power minus alpha y. So, this looks like this, alpha minus q e to the power minus alpha plus q to I. Okay. So, that is the variation of u in the free stream, and this is where you see the benefit of this compound matrix method comes out, because in the original problem we had a fundamental mode which the admissible path were going at this rate, but the solution was problematic because mod q by mod alpha is very large here. In defining this new sets of variable, we change the variation. Now, you see the variation is given by this quantity e to the power alpha plus q y with a minus sign embedded there. You would see that that would be the situation for all the 6 variables. All the 6 variables would have identical variation in the free stream. So, what it tells us that by adopting this procedure, we have been able to remove the stiffness of the problem. Once we have done that, then what we could do? We could adopt any of the methods which work for normal non-stiff equation, we can use it here, right. So, that is the whole idea in the compound matrix method, and what you would find that what I have shown here z1 going to for z1 y going to infinity, it goes like this. Please go ahead and do it and check for yourself. This will be nothing but minus and so on and so forth. So, what we could do is we have a estimate for the qualitative variation of these functions with y. So, what I could do is I can see a common factor here appearing. So, I could factor it out from all the quantities, right. So, that is what I did here. We did z1 equal to 1 here. Okay. If I do that, immediately z2 becomes minus of alpha plus q, and you check it out for yourself that z3 will be again alpha square plus alpha q plus q square, and so on and so forth. So, that is your starting solution. That is what I said, that you start off with the solution, those are given here z1 to z6, and then you keep marching, okay, and come to the wall and check what is the value of z1. If z1 happens to be 0, you have an eigenvalue. If z1 is non-zero, then that alpha is not your eigenvalue. So, you would reassign a value to alpha and do this process. And how do you reassign such a thing? Well, we know one of the standard technique is to use Newton-Raphson method. I think you would have heard of, even if you haven't, pick up any elementary book on numerical analysis, and you will see we talk about Newton-Raphson search. And that will tell you how to obtain these eigenvalues. Well, there are various other ways. We do not actually use Newton-Raphson method. We have a better way of finding it out, but I am not going to spend any more time. But what you notice here, that here is a clear example where stiffness of the problem has completely been eliminated, and you have a set of first order ODEs given like this, and you can use your RK4 method that we just now talked about in the last class, right. So, you can see life can be made very simple by doing little bit of work on the desk, evaluating all this compound matrix variables, working out this initial conditions, and write out a simple solver. People waited for 70, 80 years to get here. So, it was quite a bit of achievement by this group of people. So, in compound matrix method, as I told you that all the variables have equal growth or decay rate, that is why we can factor out the stiffness of the problem. Okay. And once the stiffness of the problem disappears, you could use any standard initial value problem routines to integrate. And as I also told you that by some other method, people have obtained this solution for the first time in 1951. So, I suppose that leaves us with the task of figuring out what the eigenfunctions are. For example, if I have the eigenvalue alpha, I could obtain the eigenfunctions which are nothing but the phi themselves, right, the phi itself. So, that could be written in terms of C1 phi 1 and C2 phi C3 phi 3. What you do is you could differentiate this few times to get phi prime, phi double prime and phi triple prime, and then you can eliminate C1 and C3. And if you eliminate those equations or those constants C1 and C3, you end up getting equations of this kind. I have just noted 2 out of 4. There are 4 possible solutions. This is a 4th order system. So, we get 4 equations. Unfortunately, the problem becomes difficult, though if the order increases. When we try to do it for a fluid flow problem coupled with heat transfer, that makes it a 6th order ODE, the original equation, and then the compound matrix variable becomes 62. Okay. So, you can see that it is somewhat more involved, and you also get a very large number of candidate eigenfunction equations. There are 4 possible solutions. So, out of those 4 possible eigenfunction equations, only these 2 are the ones which work. The other 2 has some problem. I do not wish to get into that part of the story. It is something which we have worked upon, and we have suggested why those 2 equations are not to be trusted. Because you see what happens, that our governing equation was a 4th order equation, but there are only 2 admissible solutions, right. So, if I look at the first equation, it is a 2nd order equation. So, it has 2 modes, and it happens that those 2 modes are the ones that we have retained. Okay. This one is a 3rd order equation, but you can immediately see that there is a solution which does not vary with phi, because it starts off with phi prime, right. If I write it as a sort of a polynomial for the operator d, so it will be d cube, d square and d. So, you can factor d out, the corresponding to that you will get a solution which does not vary with y. So, you can immediately see one mode is neutral, it does not vary with y, whereas the other 2 modes that you retain, they are the ones that you wanted them to be there. Okay. What happens, those other 2 equations actually are quite dangerous, because they involve some spurious numerical modes, those which will be something like alpha plus q and all kinds of, or plus alpha root. So, what happens is with this statement I will stop talking about compound matrix method and stiff differential equation. You would also notice one curious fact is that if your system is defined by a 2nd order ODE, your compound matrix method is very easy to work out. You will find out that it converts into a single equation. So, for a 2nd order system, you have a benefit. 4th order, you actually go from 4th order to 6th order system. For a 6th order system, you go to 62 equations, and it complicates with a multi-physics problem, because suppose you are talking about plasma control of flows, then you would be talking about the Maxwell's equation, and the order of the system keeps increasing. So, you probably go from 6th to 8th order, and then you can see these problems of number of equations increasing rapidly can hurt, but at the same time you do not have any alternative, because this is such a nice and clean method. The other possible way of solving stiff differential equations are fraught with danger. I mean, it does not come as easily as what you can get here. I think with this we should stop our discussion on ODE. From the next class we will be starting to talk about PD. That is where the major interest lies, because the original governing equations in most of the cases are governed by partial differential equations. So, we will begin talking about classification of PDEs. The PDEs of course are not, as you can get in a single basket, that what we could do with for ODEs, although we have seen there are variations, right. We have classified in terms of initial boundary value problem, we talked about stiff and non-stiff problem, but PDEs are much more colorful, gives you a lot of room to maneuver, and there are very interesting aspects of solutions of PDEs. Having said that, I would also add that we would not follow the classical route of solving. That is a promise which I would like to make today, and you will see as we go along that we will not be classifying them as you may have done in your other math course in terms of parabolic, elliptic and hyperbolic. Those are old hat. We have to do something better, and we can do, we will talk about that. Okay. So, I think I will stop here.